why humanity should study exoplanets. And I should introduce myself. I work at Copernicus Science Center currently in Warsaw, but I'm also an astronomer, and I still work as an astronomer, supporting other astronomers in looking for new planets outside of the solar system. If you were wondering what is the definition of exoplanet, exoplanet basically means a planet outside. That's the exo part. So the planet outside of the solar system. And why humanity should search for those? Now, I kind of figured there are 4 main reasons for that. One, and I don't think I have to spend a lot of time on that, so let's just get it out of the way very quickly. Planets are a big deal for a couple of reasons. Some people think they're a huge, huge deal and argue even now whether Pluto, for example, should still be a planet or not, according to one definition or another. To be honest, I do not care that much. Pluto is a planet, a minor planet, a dwarf planet, whatever you call it. It's a small round body far away in the solar system. But why I care about planets, why I think planets are a big deal, is that most of the time when we think about our solar system, we think of something like that. This is the picture you typically see in school, but also online, other places. And you kind of get used to the idea, hey, there's lots of planets in our solar system, places where we could go to and explore, etc., etc. But actually, most of the solar system is empty. If you put all the planets together, it turns out that most of this big circle, the orbit of Neptune, there's not too much stuff there. Now, if I ask PowerPoint to scale planets to how big they actually are, you end up with this. Literally, you cannot see the planets anymore. I asked PowerPoint to literally scale all of them, including the sun as well, to the size they actually are. And it turned out that they literally disappear, everything including the sun. So that's just our solar system, right? You could be saying, well, there's planets outside. Yeah, well, this is, for example, the image you take of the solar system from almost outside of it. This is the famous family portrait of planets within our solar system taken by the Voyager probe as it was approaching the end of the solar system. And you can see in here there's Jupiter, Earth, Venus, Saturn, Uranus, etc., zoomed in. In here you can see only letters saying, well, Saturn is kind of here if you zoom in very closely. Now, if I put that in the perspective of the previous image, this is solar system. And you can barely see now the letters that signify that if you keep zooming roughly around here, you'll find a very tiny Saturn there. So literally planets in space take up a tiniest amount of space. Now, if you go further outside of the solar system, for example, to the nearest star, and the nearest star that has a planet next to it, Proxima Centauri, which is here, you'll find that there's over 40 billion kilometers between us and this nearest star system. And just to let you sink in how much empty space there is in the universe, let me switch off all the signs. I don't know if you can see very well. That's our solar system, again, to scale. And then there are 2 more stars, well, 3 more stars really in there. But you cannot see 2 of them. This dot in here is actually 2 stars. And there is at least 1 planet there. So I just wanted to tell you, when it comes to the question, why should we search for exoplanets? Because planets are a big deal. Everything that we as humans can do, like the blank canvas for us to conduct our activities in, is basically planets. And there's not too many of them out there in the vastness of space. Now, why should we also search for them? Because I think it ties to the age-old question of life in the universe. And I think this is a question that kind of has been with us almost forever. And I don't know how many of you have imagined or watched a sci-fi show or read a sci-fi book or just literally thought about that. How many planets could there be out there with some sort of life on them? And we kind of typically imagine things like that, different planets, different sizes, maybe similar to Earth, maybe totally different, maybe typical alien life, maybe other bipedals walking around, maybe completely different thinking crystals, etc. And this has been with us for a very, very long time. Already in the 1500s, there was this guy called Giordano Bruno in Italy, a friar, who kept thinking about whether there could be planets outside of the solar system, whether there could be life there. And he said already in 1584, in this book, he said, "For there is a single general space, a single vast immensity, which we may freely call void. In it are innumerable globes like this one on which we live and grow. This space we declare to be infinite, since neither reason, convenience, possibility, sense perception, nor nature assign to it a limit. In it are an infinity of worlds of the same kind as our own." So already back in the 1500s, there was a guy claiming he thinks there are exoplanets out there, and there is an infinite amount of exoplanets out there, and that they are similar to our planet. So to me, this says that to us, to humanity, it is kind of obvious that planets are there. And it's, again, I think quite obvious to then figure out we should go and explore them. Now, how many there are? Is there actually a point to searching for them? Now, I showed this image already here 2 months ago when I was talking about space missions. And this is basically the entire universe as seen from Earth. However, I created out of it a map which has a sort of coordinates. This is up and down coordinates, minus 90 degrees to plus 90 degrees, and 0 to 360 degrees spinning around. So these are the stars that we can see. Now, how many planets are there? Well, 2 months ago, I was here showing this graph, saying that there are 3,801 planets that we have already discovered outside of the solar system. And there are some groupings. For example, you can see there's a whole bunch of planets there, almost 2,000, just in one location, because one space mission discovered so many of them in just this one place. But there's almost 1,000 and more dispersed everywhere else. So you can see, basically, the universe is filled with planets. And these are only the ones we've discovered. According to the statistics that we now get for our galaxy, it turns out we think in our galaxy of 100 billion stars, there should be about, give or take, 100 billion planets. Only in our galaxy. And then you think about billions of galaxies and how many planets are there. So in average, there should be about 1 planet per 1 star in our galaxy. But don't let it mislead you. 1 star per 1 planet means, well, obviously there are planetary systems, so there's going to be a star and 7 planets around it, and then there are going to be stars with no planets next to them. But this was 2 months ago. And I told you 2 months ago, the ones that were here, that we are discovering planets quite quickly. So since the last time I was here, we've already discovered 23 new planets. So these are some of the new ones. So what I put in here are the new ones and the ones we had to update. Because, for example, sometimes we discover new planets in the solar systems we already know about. And sometimes we discover that we were wrong about some of the other planets and we need to update information on them. And this is something you haven't seen if you were here last time. This is a map of our galactic neighborhood. Us, Earth, in the middle, and we are surrounded by planets that we have discovered so far. You can see this clump, these 2,000 planets discovered here along this path. That's because there was, as I said, a space mission looking specifically in this direction for a long time. There was another space mission looking in this direction. Everything else we've been discovering mostly using ground-based telescopes. And you might be thinking, well, are there no planets here? And are there no planets there? And the answer is, yeah, most likely there are. Unfortunately, we are not good enough to easily search for planets still outside of this sphere. Our techniques are only getting better and better every year, so we will likely be discovering more planets further out as well. But that's just discovering. So basically counting. We could be looking at stars and saying, oh, there is 100 billion stars in the sky, but we know nothing about stars. We could be thinking they're just dots. But I think humanity should study exoplanets because we can learn so much about them. They're not just faceless dots for us. We don't just count numbers and thousands. I won't be very satisfied if I come back here in 2 years' time and say, and now we have 10,000 planets, hooray, and in 2 years more we have 15,000, etc. That would be boring. There's just accountancy, a space accountancy of sorts. However, we can learn a lot about their features, about their characteristics. We can get to know them. So for example, since 2013, thanks to help from Hubble Space Telescope, we can figure out now the colors of planets we're looking at. So you can see here are 4 planets that we've figured out the colors of. There is one in blue, there is one in magenta, there's one that's completely red, and if you cannot see it, I'm not surprised, there's one there. It's almost entirely black. It's so dark, in fact, that it reflects only 1% of sunlight that gets to it. So if you were standing next to it, you would be thinking it's almost entirely black. But we can learn more. We've learned that some of the planets that we have been exploring actually have magnetic fields, like our Earth does. So you're already thinking, well, they have magnetic fields, they have some protection from their own stars, so potentially, maybe protecting life as well. More, we found planets that I'm surprised how much we know about some of them. We used the Spitzer Space Telescope in 2015 to find a planet that has the entire surface covered in volcanoes. You can see it here on the bottom, if you can see it here on the bottom. If not, there is a very red planet in here. If you've seen one of the newest Star Wars films, yeah, there was a planet called Mustafar, and that's very, very similar to Mustafar. However, it has this very quirky mechanism working on it. It is filled with volcanoes that put out so much dust into its atmosphere, it actually cuts off the entire planet from its sun for some time. It blocks the sunlight. And when you block the sunlight, you still have the volcanic activity heating up the planet, but not that much incident sunlight. So the planet starts cooling down. And when it starts cooling down, some of the lava on top of it starts solidifying. So it turns into this slightly blacker one. But when this solidifies, there's less volcanic activity as a result as well. There's more dust being kicked up into space, and the skies clear up. So then the planet starts warming up again, and the cycle repeats, just scratching the surface. I think one of the most exciting things we can learn about exoplanets now is we can try and figure out the composition of their atmospheres. And that's crucial. To do that, we use something called transmission spectroscopy. So we look at when the light from a star passes through the atmosphere of a planet, and it gives us this sort of a spectrum. So basically, light in different colors of different intensities. And from these graphs, we can figure out what molecules are there in atmospheres of other planets, even hundreds of light years away from us. So for example, you can see here we've discovered titanium oxide on some of the planets. We found water on some of the planets outside of the solar system. And what you see in here on the right is just a selection of planets where we have found water. And interestingly enough, these discoveries were made in 2013. Some of the first water we were able to confirm on Mars in liquid state was roughly from around the same period. So I was absolutely stunned to keep reading every year what we were discovering on Mars and other moons in the solar system, and at the same time reading on and basically conducting studies related to water outside of the solar system. And this is just a selection of 9 worlds, and as you can see, they are very different. These guys on top are basically huge gas giants, and we found water there. This is a Neptune-sized planet, and we found water there. And these are Earth-sized planets, and there seems to be water there as well. Now, more interestingly, this planet called WASP-12b is being consumed by its star. It's heated up to a very high degree, and its atmosphere is being sucked into its star. And we found water there. So it seems like there's quite a lot of water out there in the universe. And not only can we learn what is the composition of atmospheres, but we can even start mapping the weather. So for example, we know that some of the planets have very clear skies, and others very cloudy ones. We can try and figure out what these clouds are made of, how reflective they are, how much they reflect incident sunlight on these planets, and how much they keep the warmth inside. So this stuff would be cooling a planet down. This stuff will be keeping the warmth kind of next to the planet and keeping it warm. We're talking about greenhouse effect here. We've even figured out whether it rains on other planets. And you can see some planets here in our solar system, and there are some bizarre planets outside. Like there's HD 189733b, the third one, where we think there could be rain made of glass. And there is ugly TR56b, where conditions are perfect for rain to be made of iron. Now, and some of my favorite planets, because these are the ones I've been studying for many years, are evaporating planets. Planets that are being eaten kind of alive by their stars. They're typically so close to their stars, they're heated up to such a high degree that their atmospheres start expanding. And when they expand outside of their own gravitational sphere of influence where their gravity wins, and the gravity from the star starts winning over. So then some of the atmosphere is being sucked into the star. It typically creates a ring around it. And that's very special for us as scientists, because what we can do is not only study the atmosphere of the planet when the light passes through this very, very thin ring around the planet. Now we have the entire ring, huge ring surrounding the planet that some of the light passes through and lets us learn more about the composition of these planets. And again, they're quite different. This one is a hot Jupiter. A Jupiter-sized planet that's strayed so close to its star, it started being eaten alive. Now, there are Neptunes as well, and this one seems to have a lot of water on it. They behave almost like huge comets. And that is my favorite ever, because this is the one I've been working on for many years. KIC 125575 or 8b, for friends KIC 2055. And the cool thing about it is this is the planet the size of Mercury. So it's tiny. It spins around, it orbits around its sun so quickly, the entire year on that planet takes 16 hours on Earth. So imagine having an entire year completing the entire orbit basically every day, and even more often than that. So it's so close, the surface of the planet heats up. Similar way to the volcano planet I mentioned to you earlier. However, here you wouldn't even have volcanoes. The surface of the planet is heated to such a degree, almost the entire surface melts. And when it starts melting, it starts spitting, again, dust into the atmosphere. It's creating its own atmosphere. And the dust is so thick that it, again, covers the entire planet and cuts it off from its star. And when it does so, again, the planet re-solidifies and stops spitting dust out, and again, the cycle repeats. So what you can see in here is it kind of looks like a massive planet-sized comet that from time to time extends its tail, and then the tail shortens and then disappears. And then it reappears and gets longer and then disappears entirely. And you can imagine how hard it is to study when you have to plan observations in astronomical observatories around the world, hoping that when you go there in about a year or year and a half's time, the comet tail will actually be there. The problem with this planet is it is so small, we cannot see it without the big tail. We can only see it when the tail is there. So then basically the planet from time to time disappears entirely. And this is very interesting to us because, as I was saying, in here we can study atmospheres of these planets because they spit out into space. But here we can actually study the surface of a planet. So we can actually see what is the planet, the solid stuff of planet, what is this made of. It's kind of almost like taking a shovel, digging it in, and then checking what the dirt is made of. So we've already figured out that this planet, for example, the surface of it, is made of, at least partially made of corundum, aluminium oxide. And to me, this was stunning. When we made this discovery, I was absolutely stunned. You know, we can start exploring what surfaces of planets outside of the solar system, hundreds of light years away, are made of. And even better, it tells us a lot about planets in our solar system. Because what you can see in here is planets being stripped to their core, getting smaller and smaller and smaller. And that means that basically we're kind of looking inside of planets. Some of those started far away from their stars, like a normal planet, maybe like Earth. And then they started migrating towards the planet, the star, and the star started eating its outer surfaces, getting deeper and deeper and deeper towards the core. And the more we find these planets, the more we explore them, the more we learn about internal composition, internal chemical composition of planets. And that will help us also to learn about internal composition of planets in our solar system. But also, quite stunningly, we started mapping surfaces of other planets. So what you can see in here are two maps that we created of, in here I'm slightly exaggerating the surface. This is the outer layer of a planet. Both of these are gas giants, so it's hard to talk about surface there. But you can see these are maps of insolation, so how much sun there is and how much heat there is in different places around this specific planet. And I don't mean this is not a model, this is not a computer model. This is actually a map we created based on data we collected from telescopes. And there is another sort of map created for this weird planet, HD 80606b, that I observed as one of my first exoplanets ever. That is such a weird planet. It has a 111-day orbit where it goes away so far away from its star, it starts freezing over, and then comes back and heats up by 1,000 degrees centigrade. So it's an insane planet. And what we've tried to do is create a map of atmospheric circulation around it and how much heat transfers between different areas of the entire planet. And all of that, all of this wealth of data and exploration we've done so far leads us to this, a list of potentially habitable planets. Because what I told you earlier is I think that some of the interest that we have in exoplanets is related to the fact that we kind of want to know whether aliens are there. We kind of want to know whether we're alone in the universe. And also, potentially, whether there are places that we can move to in the future. And I'm not going to even touch on Mars, because Robert Zubrin is here, and I bet he's going to tell you so much more about that. But if we were to venture outside of our solar system, where would we go? Where would be places that we think potentially could be habitable? And mark this word, potentially doesn't mean they are habitable. We think, basing on all the data we have right now, all we've learned about these planets, their distance from their stars, etc., that they potentially could be habitable. And by that I mean there potentially could be water on the surface of these planets. But that's just a very narrow definition of habitability, right? If you think of, for example, aliens out there that have very different physiology to ours, maybe they don't need water. Maybe there is an entire life out there that's built around using methane rather than water. And then they wouldn't need water on the surface of their planets, they would need methane. So this is just a very narrow definition of what habitability means, specifically tailored to us human beings. And you can see these are some of the best bets that we found so far. If you wanted to learn about more planets that could be habitable, go to the Planet Habitability Laboratory, which there is a website about that. And what they do is they keep evaluating and re-evaluating planets out there to try and figure out how habitable they are. And this is the current number of potentially habitable exoplanets out there in the universe. Different sizes, so Mars size, Earth size, super Earth, or mini Neptune, and in total. Out of these numbers, they think 55 is the optimistic number. The more conservative number nowadays is about 12. But again, we started searching only about 20 years ago. So, or we started finding planets only about 20 years ago. So since then, we've discovered potentially 55 habitable planets. There will be more in the future. And now, when I'm on the topic of habitability, let's move to another point why I think we should study exoplanets. And I think that because learning about other planets gives us perspective on our planet. And specifically, the habitability question is important, because if we learn what makes other planets habitable, we can start thinking about what makes our planet habitable. And I think this is one of the most important questions that we can ask nowadays. Now, going back to our very crude, rudimentary picture of our solar system, I'll stick to it for now because it's nice and planets are big, so you can see them. So, when I talk about habitability, what I usually mean is that when planets are too close to their star, it is too warm there. So if you had any surface water, it would basically evaporate and potentially escape into space, or it would have to be hidden somewhere underground very deep. So in this area, for example, where you can see that's Mercury, that's Venus, should be too hot for water to exist on the surface of a planet, so potentially too hard for life to exist. Now, if you go too far, it becomes too cold, so all the water is frozen. Now, if you are in just the right distance, you're in the so-called habitable zone. Now, this is a very loose definition, because habitable zones are not given once and for all. So according to sort of a definition that we have now, if you imagine an ideal planet, just a normal rocky planet, and you ask a question, could there be water just basically swimming around in pools, then this is where you should find water. Maybe on Venus, definitely on Earth, maybe on Mars. Now, obviously, you don't have these ideal situations. Most of the time, you have some other things that you have to take into account as well. So, for example, I'll give you just two features of a planet that you might want to consider when thinking about habitability. On one hand, you have the greenhouse effect. That's something that warms the planet up, or rather, keeps the warmth of the planet there. It keeps the warmth from escaping into space. So that's a blanket of clouds, for example, surrounding our planet and other planets as well. On the other hand, the cooling effect could be albedo. Albedo is basically reflectivity of a surface of the planet, or, for example, of a cloud cover. If you increase albedo, for example, when I talked to you earlier about the volcano planet, the evaporating planet, if you put so much, for example, bright dust out there, it reflects 100% of sunlight back into space, you cool the planet down considerably. So I'll be using just these two features. There's many more. I'll just be using these two features to show how they have an impact on a habitable zone. For example, if you switch off the greenhouse effect on the planet, but keep the albedo up, what happens is the habitable zone moves closer to the star. Because all of a sudden you still have the cooling effect, but you don't have the warming effect. So you can be closer to a sort of radiation and spitting out star. So you can see in here, for example, if there was no greenhouse effect, only the albedo, then Venus could become a habitable planet. Currently, it doesn't seem to be very habitable. It has a very strong greenhouse effect, which warms it up considerably. Earth could get to the outer border of habitability, but Mars would be totally outside. And you wouldn't be surprised to hear there is not that much greenhouse effect on Mars. Now you could go in the opposite direction as well. So switch off the albedo, make, for example, the planet darker, or remove the clouds, and increase the greenhouse effect. And you get the opposite situation. The habitability zone moves outwards from the planet. There is something warming it, so you can be in the typically cold zone, but there is nothing cooling it, so you cannot be so close as before. And again, we end up with Venus now being outside of a habitable zone. It's too warm. Earth is still in it, but Mars, all of a sudden, is bang in the middle. You could, for example, one idea for terraforming Mars is to put a lot of CO2 there, create some sort of rudimentary greenhouse effect and start warming the planet up. Now we can go into overdrive, increase the greenhouse effect even more. But what could happen then is, well, you put another planet outside of habitable zone, and it's our Earth. You could imagine a situation where you have a runaway greenhouse effect, which keeps increasing and increasing and increasing. It pushes the habitable zone out so far, we are not in it anymore. So that's just two factors worth considering. But the problem is, it's really hard to talk about these things, the climate change, etc., basing our experience on just one planet. You know, typically when you talk about the scientific method, how scientists work, well, what we do is we create a hypothesis, a model of the world, and then go and test it, typically by conducting experiments. The trouble is, it's really hard to conduct experiments with planets. You can't do too much to them. And also when it comes to planets similar to our Earth, if the only planet we were conducting experiments on was our Earth, that wouldn't be, first of all, very, very scientific, and secondly, very safe. I mean, what if the experiment goes wrong? Then you have nothing left to experiment on, and no life on our planet to experiment. So, and this is kind of the situation we are in if we don't explore planets outside. We have one planet to test all our hypotheses on. And I think we kind of are currently in the middle of a grand experiment. Whenever I hear conversations about climate change, etc., it's basically an experiment conducted on one planet. And I think what would work best is, for example, to have a second one. A planet out there in the universe that's a copy of our planet. And then we can try and experiment with. For example, our planet we add CO2 to and see what happens when we increase the greenhouse effect. The other one, not. Or the other way around. Increase the greenhouse effect on the other planet, we stay where we are and see what happens. If it becomes unsafe on the other planet, then we know, okay, this is not the right way to go. Let's try something else. But, well, you could say, well, a sample of two planets, that's not enough. And I agree. That's why I think we should search for even more planets. That's the 3,000 planets we've discovered so far, and a large percentage of those are small planets as well. The more we find analogs to our Earth, and the more we look at them and figure out what's happening there, the more we learn about what would happen if we repeated the same experiment here on Earth. Now, what can we learn from this wealth of planets out there is obviously not only a question of CO2, for example. I'll give you one example. For example, if you wanted to figure out how the temperature changes when you move closer and further away from your star, if you had only access to planet in our solar system, well, if you were a clever scientist, you could say, well, let's see, this distance from the star, we have Earth and Mars. That distance, we have Mercury and Venus. So clearly there is some sort of a model that goes through these points. The further you are from the star, the lower the temperature, and it drops very quickly. There is some sort of a boundary here. If you are here, the temperature is high. If you're there, the temperature is low. Boom, a quick drop. So if you move even further away, you end up here. If you move closer, you end up here. And Venus is sort of in a natural position because it's right next to Mercury, so yeah, everything's fine. This is how solar systems work, right? But if you start studying other planets and add them to the same graph, well, it turns out that almost every other Earth-like planet that we discovered outside of the solar system, the sizes here are indicative of the sizes of the planets. So planets the same size as Earth are the same size, or roughly the same size as Earth. You find that, well, actually the trend is slightly different. The trend is here. So most planets are along this line. And Venus and Mercury stick out there. There's something different about them, something different to most of the other planets we discovered outside of the solar system. Now, Mercury is weird because it's smaller than most of them. So we don't know whether, if you look just at small planets, maybe you would have a different line. But Venus is the size of many other planets like here. And they should be, Venus literally, judging by its distance to its star and judging by its size, etc., it kind of should be there. But it isn't. So what makes it go up there? Well, the strange, weird, hyper greenhouse effect it has on its surface. So this is just one example I wanted to show you that allows us to learn more about the planets in our solar system by putting them in perspective of planets outside. Now, the last reason why I think we should study exoplanets. And it's a sort of a broad and I would say philosophical one. I think we should study exoplanets because it's kind of in our nature. I think it's in our nature to go beyond what we know and explore new things. And we've explored most of our surface of our planet. There is still a lot to explore when it comes to biodiversity, finding new species, exploring the oceans that we still haven't explored as well as we should. But outside of that, I have this feeling, and I have many of you as well, that our Earth, we kind of have it covered. And it would be interesting now to go and start exploring new worlds. And there are other worlds in our solar system where I think we can go and land and potentially explore and live on, etc., etc. But fortunately, you can keep in your mind always that after we go and explore in our solar system and settle all the planets we can, there's still a wealth of other bizarre worlds out there that we will be learning new information about for years to come. Thank you.
As we know, a few months ago, they sent to space TESS telescope. Is there any news and some interesting information? Thank you.
I think it will be still in the commissioning phase. Typically when you send a telescope into space, what you do is start first calibrating it, learning about the response you get from it. So you take images of things you recognize in the sky and then start learning whether what you can see matches with what you know already. So typically there's a commissioning phase taking a couple of months, and only then you start acquiring scientific data. So we expect TESS to find thousands of new planets. But it's going to take years as well. The idea of TESS is, as you might know, but others might know, TESS will be basically scanning the sky in search for exoplanets. So we first scan one hemisphere, and then twist around and scan the other hemisphere, and then keep repeating that. And it's going to stay on every part of the sky for, I think, a couple of weeks. So we will be waiting for quite a long time before we start getting information about at least some of the long period planets. But yeah, I'm looking forward to seeing the first data coming back from it that will be used for scientific purposes. Second thing to bear in mind is after they do get the data, typically what scientists, exoplanetologists nowadays do is we combine a number of observations and then publish one large paper saying we've discovered, for example, 100 or 1,000 planets. That's typically what I found American exoplanetologists do nowadays. Wait for a year and a half and then publish a large paper saying we found 1,000 new planets. For example, we in Europe tend to celebrate every single discovery we make. Not because there are so few of them, I think we're just so overexcited about them. So you can expect a new paper every couple of months from our researchers.